let's consider the possible cases that we could encounter while doing a hypothesis test. So let's say for some magical reason we know, well, we don't need to say that we know this, but this is a possible case, right? Is the null hypothesis is true. And if the null hypothesis is true, there are two things that can happen in the hypothesis test. Either we fail to reject it, the null hypothesis, or we reject the null hypothesis. Now, if the null hypothesis is true and we fail to reject it, this is the correct decision. This is the correct decision. In a perfect world, we would be making only the correct decision. But there is some wiggle room, potentially. In a hypothesis test, it is possible that you are unlucky and you observe a statistical value that is extremely unlikely to occur, which might cause you to reject the null hypothesis even though it is true. This is an error. And we call this type 1 error. This is referred to as type 1 error. Now, what if, in actuality, the null hypothesis is false? Then you want to be rejecting it, and this is the correct decision. If the null hypothesis is false, we would be rejecting it. So there is another error that can happen, and that is that the null hypothesis is in fact false, but you fail to reject the null hypothesis. This is type 2 error. Type 2 error. All right, type 2 error. So let's take a look at these a little more closely. Type 1 error, we tend to use the letter alpha to represent then the probability of committing a type 1 error. Probability of committing a type 1 error. This is also referred to as the level of significance of the test. Level of significance. Level of significance. We tend to use the letter beta to talk about the probability of a type 2 error. Type 2 error. Beta. Probability of failing to reject H not when it in fact is false. The complement of this 1 minus beta is called the power of the test. Power of the test. It's called the power of the test. So what's the power of the test? This is often something we are concerned with, is rather than just the probability of committing a type 2 error, but we might say, what is the power of the test, right? What is this probability? The power of the test, this is the complement of committing a type 2 error. That is actually, the probability of getting that correct decision. This is the probability that you reject the null hypothesis given the null hypothesis is in fact false. Given the null hypothesis is in fact false. So these are the possible, in our two-way table, either the null hypothesis is true or false. Okay? And so oftentimes what a statistician will do is set up the level of significance first, and you actually want to do this before you proceed with your test, and decide, how much type error are you willing to accept? We can control that, and once that's determined, right? If we're not willing to accept much type 1 error, that's fine. We can control that. And so what I want to do is take a look at an example where we get to talk a little bit about the actual likelihood of committing some of these errors and computing some of these probabilities. So I will scroll way down here where I have this first example set up. A type of cold vaccine is known to be only 25% effective after a period of 2 years. We want to know if a new vaccine is better. So we apply the new vaccine to 20 individuals and record X. X is counting the number of individuals for which the new vaccine still works after 2 years. So let's define the null hypothesis to be the two vaccines are equally useful. The two vaccines would be equally useful. And the alternative hypothesis is that the new vaccine is better. All right, so what does this actually mean when we say the two vaccines are equally useful? Well, the original vaccine was 25% effective after a period of 2 years. So if the two vaccines are equal, then the probability for the new vaccine should be 25% success after 2 years, should be 25% for the new vaccine. What would be the alternative? The new vaccine is better. If the new vaccine is better, then we would interpret that where P is greater than 25%. We want it to work for more than 25% after 2 years. So our null hypothesis is that the probability is equal 25%. The alternative is that it is greater than 25%. So let's suppose that we will reject the null hypothesis if X is greater than 8. We tested on 20 individuals and decided that we will reject the null hypothesis if more than 8 individuals the vaccine is still working for them after 2 years. Let's find alpha, the probability of a type 1 error with these conditions. Let's find alpha, the probability of type 1 error given these conditions. So what is alpha? That is the probability of rejecting the null hypothesis given that it is true, even though H naught is true. This is then the probability of, so what do we reject it? We reject it when X is greater than 8. That's the probability that X is greater than 8 when P is equal to 0.25. That is the probability that X is greater than 8 when P is equal to 0.25. Well, if we assume that P is 0.25 and we want the probability that X is greater than 8, think about what's the likelihood that the vaccine works for any individual? These individual probabilities are binomial. We have 20 individuals, so there's 20 trials, and the assumption is the success rate is 25%. We want to know, then, what's the probability that type 1 error? That would be computing the sum of these as we go from 9 to 20. 9 to 20. Right? Right? This would be the probability that X is greater than or equal to 9 when it is binomial with N equals 20 and P equals 0.25. This is exactly what we want. So how do we figure out the probability that X is greater than or equal to 9? Well, this is binomial, right? And so we can go ahead and take a look at the table here. How would one compute this probability from 9 to 20? There's a couple ways that you could do this. One might consider the complement. That would be the probability that X is less than or equal to 8. Oh, that's the complement, so we would want 1 minus that. 1 minus the probability that X is less than or equal to 8. The point of this is not necessarily to practice our binomial probabilities, so I'm not going to spend too much time on this. Let's go see if we can find the table when N is 20 and P is a quarter. Do we have that ready to go here? I do not. So let me pull up my table. Go ahead and take a look in the back of your book. And here we go. Where's our binomial table? Poisson. Binomial. N is 20. P is 0.25. And we're looking at a complement of less than or equal to 8. That's 0.9591. 0.591 is the probability that I'm pulling right there. And so the probability of committing a type 1 error then is 0.0409, or about 4.09%. About 4% is what we've done, what we've decided there. That is our type 1 error, okay? There are a couple ways this actually can happen in practice. In one sense, someone can set the significance level to be like 4%, and then you can go backwards and say, well, what is the equivalent X value that would do that, right? Or, someone could set this, significance level and say, we're willing to accept a type 1 error of 5%. So what is the X value that would allow us a type 1 error of 5%, and kind of try to reverse engineer that, right? And that's common, right? Which can be done by looking at the table there when n is 20. Or we can specify the number of individuals that we are willing to accept as well. That is our alpha, our type 1 error. What about the type 2 stuff? Remember, type 2 error is the probability that you fail to reject H0 even though it is false. All right? So this is a little more interesting. If we want to find beta, if we want to find beta, we need to look at a specific alternative hypothesis. Look at a specific alternative hypothesis. We look at a specific alternative hypothesis, right? So what's a valid alternative hypothesis? Any p-value greater than 25% can work, right? But we can't compute any of these probabilities unless we have a specific value for p. So let's say we look at the specific alternative hypothesis that the true probability of success is 50%, right? Then we can calculate beta, the probability of a type 2 error. In this case, if p is 50%, type 2 error, right? Type 2 error is the probability that you fail to reject given it's false. So we fail to reject, which would mean X is less than or equal to 8. Given it's false, we fail to reject a null hypothesis when p equals 50%. When p equals 50%. And that we can calculate. This is the sum as X goes from 0 to 8 of our binomial tests with 20 and a success probability now of half. And we can look that up in the tables, and we should quickly find that is 2.517. Okay? This type 2 error beta will change depending on what the specific alternative hypothesis is, right? If I say, what is the type 2 error when the alternative is 40%, I'm going to get a different value for beta, right? I'm going to get a different value for beta, right? So this is one of the reasons why we bring up the word power in the test, right? The power of the test. How do we interpret the power of the test? Remember, the power of the test is 1 minus this. The power of the test then would be 74.93%. That's 1 minus 25.17%. This is the power of the test, 74.93%. So how do we interpret that, right? This is a success. This is the probability that we make a correct decision. The test will properly reject the null hypothesis that the success probability is 25%. It'll properly reject it about 75% of the time. of the time if the true value is 50%. Right? If the true value is 50%, then we will properly reject the null hypothesis about 75% of the time. Okay? And that's how we can interpret that. All right? And so in terms of power, right, that's not very powerful, right? Ideally, you'd want a test that has a very low type 1 error, and you'd want one that's very powerful for potential likely cases, right? 50% is much different than 25%. I would ideally want a more powerful test that would properly reject it, maybe 90% or 95% of the time, right? And that can sort of help guide what you might be thinking about as for your level of significance. There's a little bit of tug and pull here, some interplay there, okay? And so maybe we want a more rigorous test, right? Maybe we want to change our value, our cutoff value here. Maybe we don't reject the null hypothesis if x is greater than 8. Maybe we see what happens as we change that, and you can set these percentages maybe where you want them based on that. That is going to do it for this video outlining how to calculate some of these errors, okay? In future videos, as you get further into this, you'll talk about actually computing or actually doing hypothesis tests. But when you do a hypothesis test, right, these constraints, the type 1 error, right, the level of significance is always determined before you run the test. You have to set these before you run the test. You can't run the test and then start choosing your errors. You need to set these before, and so it's good to get a feel of how to calculate the power of a test and the level of significance of a test as well. We'll see you in future videos.